You can go ahead.
Okay, welcome everyone to this new ICMM IFIMAC joint seminar. Our speaker today is Félix Zamora, but before introducing him properly, I remind you to please keep your microphones mute. And our speaker today is happy to be interrupted and get questions on the way. So please just unmute yourselves and make the questions you may have, trying to find the right spot to make them. And as usual, we will have some minutes at the end of the talk, so you can also keep uh, further questions for the question and answer uh, uh, interchange at the end of the talk. So Félix Zamora is full professor here in La Universidad Autónoma de Madrid in the Department of Inorganic Chemistry, but he is also a member of the IMDEA Nanoscience Center here in campus, the Institute of Advanced Research in Chemical Sciences, and the Condensed Matter Physics Center, IFIMAC, here in campus too. He did his PhD in this institution and held postdoctoral positions in Dortmund, Germany, and Virginia, the US. And he is or has been recently visiting professor in Newcastle, in the UK, and Singapore. He sits in the editorial board of different high-impact journals in the field of chemistry, well, in the multidisciplinary fields he works on. He's the head of the nanomaterials laboratory, nanomatter.s. His research activity has given rise to more than 200 papers in areas ranging from nanoscience to material science, from multidisciplinary chemistry to inorganic chemistry. Apart from the relevance of his research, we will heard about in this talk, Félix has developed technological projects with companies such as Abengoa or Repsol, and he's scientific advisor or even founder of a spin-off companies like NanoInnova, Porous Ink Technologies, and 14 Energies. In 2014, Félix got the Research Excellence Award by the Spanish Royal Society of Chemistry, and last year he was appointed as Distinguished Professor with the Mention of Excellence of the Excellent Program for University Professors of the Comunidad Autónoma de Madrid. Today, Félix is going to talk us about antimony. The original title of his talk was Evolution in Uses of Antimony from Ancient Egyptian queen makeup to new 2D materials. I think he has changed it a little bit, but now, Félix, the stream is yours, so please go ahead.
So after this long presentation, Antonio, I think I'm done. I don't have to add any other thing. No, yeah. Thank you very much for the introduction and also for the opportunity that you and the organizers give me in order to present part of our research. Yeah, as Antonio said, yeah, I was pretty optimistic at the beginning, and when he asked me for a title, I thought, okay, let's try to make a long revision of antimony. But later, I was, after I reconsidered, yeah, I think I'm going to be a little bit more brief, and I'm going to focus on the antimony for the development of new 2D materials. In any case, if we have time or you have time, I will be fully available to discuss about the original title. So I have the slides at the end of my talk. So yeah, let me extend thanks to this group of people that joined the low dimensional nanomaterials research group. Is a group that is joined by these two subgroups. The one led by Julio Gomez, Nanoforces, and my own group, Nanomaterials Lab. As Antonio said in the introduction, so I'm in organic chemistry. So yeah, initially our aim is to provide most of you to provide you with new nanomaterials, and for that we initially focus in the use of something that we call coordination polymers, with the aim to by one hand to get new stimuli response materials. And by the other, for years, we were trying to provide with new components for molecular electronics. So as is represented somehow here in this slide. So we try to use coordination polymers to provide indeed with new molecular wires. And for that, we look for the components, the proper components of the coordination polymers to grow to one-dimensional architectures. Indeed, a coordination polymer is formed by two building blocks, initial building blocks. One is the what we call metal entity. In the simple is a methyl ion, and the other is a molecule. So it's a kind of we call Lego chemistry. So if you find the proper building blocks, you can, meaning reactivity, geometries, you can build up this kind of 1D structures. But you can also extend these structures to 2D and eventually even 3D structures. So you can, combining these building blocks, so you can build up almost whatever you want. So yeah, and that's the reason why we move from 1D to 2D structures with the idea to provide with new 2D materials having this advantage, the chemical design of structures. So not only that, but you can properly combine building blocks and then you will end up with additional functionalities, okay? So, yeah, due to the interactions that we have with the group of Julio Gomez, we also, part of my group is also dealing with the production of something that we call purely inorganic 2D materials, as is the case of graphene. So Julio was very much interested years ago in graphene. And then, yeah, we decided to do something in graphene, liquid phase exfoliation, and then we moved further and we have developed some other elements that can, form new 2D materials. So as is the case of the antimony, of course. Yeah, so as you know from graphene, so many exciting properties, not only physical properties, but also chemical properties came to the literature. And then, yeah, in order to fulfill this toolbox and analyze new properties for new 2D materials, we were trying, all of us, we were trying to develop new alternatives to graphene. In here, I try to summarize, yeah, some of the major groups that we have right now in order to form 2D materials. So we call MXenes mainly to metal carbide. So this is a group. Other group is based on transition metal decalcogenides. So we had many talks about that. So for instance, Andrés Castellanos was talking about the use of these transition metal decalcogenides. We have another group based on nitrides, either with they are binary combinations, either with non-metal elements and as well with metallic elements. Then we have a group that we call metal-organic materials, which are formed by coordination polymers and a subgroup that we call metal-organic frameworks or MOFs. This group is a particular kind of coordination polymers which show porosity in the structure, okay? And if you combine just molecules, organic molecules, we have another subgroup that we call covalent organic frameworks. Yeah, but probably the most simple one is the group that we call Exenes, which is formed, as you can see here, just by elements. Okay, so yeah, then if you check, in order to form these Exenes, to the architectures, you have to check the periodic table and look for allotrope of elements having this kind of 2D van der Waals crystals. As is the case for the, of course, for the carbon, it was the first. You have the graphite, is a carbon allotrope, and then starting from graphite, you can isolate graphene. But if you check carefully, you realize that this group is particularly interesting for this to isolate Exenes. So the fitting group of elements of the periodic table. Yeah, and in here, of course, we have located the antimony. But in any case, how we can prepare 2D materials? So you have in principle, two alternatives. So first, we call bottom-up approaches, which are based essentially in the use of chemical reactions. Of course, you have to do a chemical reaction, but you have to adjust a lot of parameters in order to properly form the 2D structure. In here, I highlight the use of chemical vapor deposition, which is particularly interesting for the case of, for instance, graphene. So we are able right now to produce graphene using these kind of ovens, chemical vapor deposition ovens, in which you have inside you can use a copper foil as a catalyst, and on the top of the copper, at the end of the day, at the end of the process, you form using these carbon sources, you can form graphene. Okay, but also you can use top-down approaches, and then you start with this kind of layered 2D materials, crystals, and then you, by means of kind of exfoliation, you end up with 2D materials. Okay, yeah, and for that, you have to start with kind of precursors, which are indeed the 2D Van der Waals crystals. And here I give you two samples. This is the case of the graphite HOPG. So the structure of HOPG is in here represented. As you can see, we have a weak interaction between layers. And then if you delaminate these crystals, so you end up with a single layer or few layers and then graphene. Okay, but it's the same case, similar case for the transition metal decalcogenate. So we have this big crystal, it's a 2D Van der Waals crystal with this structure, and you can delaminate them, and you end up with these few layers of materials, or single layer. Okay, and how you can do that? So if we start with these Van der Waals crystals, you have to delaminate. And then we mainly use micromechanical exfoliation based on the use of these kind of scotch tapes or kind of adhesive tapes anyway. And then upon several cycles of exfoliation, you end up with a few on the top of the tape, you end up with a few or single layers of our material. Andrés Castellanos, some few weeks ago, do this in streaming. So you can revisit the video from Andrés if you are interested on this particular field. But in any case, you can transfer what you have on the tape onto several substrates and analyze the result by using different kind of microscopies. For instance, sometimes optical microscopy or eventually AFM, okay, atomic force microscopy. So yeah, and starting from that, you can analyze not only morphologies, but also you can analyze physical properties, and eventually you can end up with kind of devices, fundamental devices. Okay, you can do also that, I mean, exfoliation, starting with the same precursors, with the same 2D Van der Waals crystals, but then doing what we call liquid phase exfoliation. For that, you have to, you start with the crystals. You can use small crystals in this case. You don't have to use these big pieces of crystals as in the case of the micromechanical delamination. And then you have to adjust a lot of experimental parameters. Just to simplify, you have to look for a proper solvent or mixture of solvents, and then a kind of energy source. And for instance, probably the most typical one is ultrasound. And yeah, I don't have, I have a video, but I don't have the possibility, okay, to show you the video. I don't know the reason why, okay, probably it's because of the laser pointer. Anyway, I follow up. And then you, yeah, this is just to show you that there is a nice revision by Valeria Nicolosi, in which they show us a nice summary of this liquid phase exfoliation, and eventually they show us how you can even prepare by combination of these dispersions, you can prepare sandwiches structures. Okay, so yeah, we have different possibilities to form to isolate 2D materials. But if you focus in potential applications, in particular for optoelectronics, then probably you want to fill up this whole band gap from 0 to up to 2 or 3. And then, yeah, the question is that typically, if you focus on this region in between, let's say, 0.5 up to 1 electron volts, yeah, you have kind of problems looking for samples that can give you this this option, but just black phosphorus. But the question with the black phosphorus is this, here is nice represented by the work of Andrés Castellanos, yeah, in which they show us that when you isolate black phosphorus on the top of some substrate, and here I think it was silicon oxide, the nanolayers of black phosphorus within the time under ambient conditions, it shows degradation, you see. So yeah, and because of oxidation and hydrolysis of this material, starting material. So yeah, from this point of view, black phosphorus somehow shows difficulties in order to provide you with a material able to form kind of 2D devices, okay? So yeah, that's the reason why we thought at the beginning that, okay, we should analyze the group in which phosphorus is located. This is the group we call pictogens to this fitting group of elements. And if you analyze properly the structure of this, of some of the allotropes of these elements, you realize that, okay, I don't know whether you are familiar with the allotropes of phosphorus, but we have many different allotropes for this element. However, this is the structure of the one having this 2D van der Waals disposition, the black phosphorus one, in which we have a weak interaction between layers, of course, but it's not the only one, the only element in this group. If we move further, if we move down in the group, we found arsenic. And arsenic shows two allotropes of interest for us because you have the isostructural one with the black phosphorus, which is the black arsenic. It's showing the same structure. But and another one which is calling gray arsenic, showing this layered structure, slightly different disposition of the atoms in the layer, and this is so structural with the one that we have for the antimony, gray antimony or beta antimony. Okay, so along the group we have different possibilities to start with materials and then delaminate them and try to form 2D materials. Yeah, the problem that I had at that time is that I couldn't find any student. I brought the arsenic. Those are the crystals from arsenic. So you believe me, you can believe me. But I couldn't find students to work with this material. I don't know the reason why. But then I should move further down in a group, and then I passed to antimony. Yeah, and we have the crystals of this material, and then okay, we started with this delamination. But you have to take into account that as far as you move down into the group, the interlayer interaction between all these allotropes, the interlayer interaction becomes stronger and stronger. Therefore, we envision problems with the exfoliation as far as you move from phosphorus to arsenic and so on. Okay, so this was the initial motivation to try to analyze the possibility to form 2D materials, starting with these antimony crystals, just to overcome the problems of stability with the black phosphorus. Okay, but additionally, we have an extra motivation because we checked the literature and we found a lot of, when we started, we found a lot of work, theoretical work, predicting exciting, band gap for this beta antimony, single layer and bilayers beta antimony. And here we summarize these, several band gaps calculated with different levels of calculation, and also a kind of exotic physical properties. So yeah, this was an additional motivation. And then we decided to start with these ideas. Okay, so let me just very briefly summarize the structure of antimony, beta antimony, because we will use later some of these parameters. This is the structure of beta antimony of this bulk crystal. So in here you can see that it's formed by layers with this disposition, thick disposition into the layer in between the atoms, and then you can observe that every single atom of one layer show every single atom is connected to 3 other antimony atoms along this layer. Okay, In here, I gave you some relevant lattice parameters that we will use for later for the material characterization. Okay, so yeah, what we did first, it was to try to produce the material following the most simple approach, which is the what we call micromechanical exfoliation. For that, in collaboration with Pablo Ares and Julio Gomez, sorry, we took the bulk crystal of beta antimony, and then using an adhesive tape upon several cycles of exfoliation, then we had a kind of a few layers on the tape, and we transferred to silicon oxide, and we analyzed what we had in these on these surfaces, on these substrates. And then using optical image, optical microscope, this is a typical image of this optical microscope. We had kind of these big layers. Those in yellow represent a big thickness in comparison with this in blue, which is a slightly, smaller in thickness. So, but we realized that when we try to characterize this blue layer, we realized that around this layer, let's say over here, if we use AFM, atomic force microscopy, we can find something that we couldn't see under the optical microscope, and these smaller layers. Okay, so we have a smaller layers that we cannot see by by optical microscope. Let's zoom in this particular small set of layers, and as you can see here, yeah, those are really small in thickness. These are really small, and if you check this height profile, this line in green, you can see that this violet layer show a thickness which is particularly small, 1.8 nanometers, which nicely correspond with isolation of a bilayer. So taking into account that we should have, because this is ambient conditions, we should have some kind of additional layers of water on the top and in the bottom of this nano layer. Okay, so yeah, this demonstrates that we were able to isolate bilayers. Okay, and yeah, additional characterization show by transmission electron microscopy show us that we have we retain the nice crystallinity, atomic resolution. And if you look at here, we have the expected parameter corresponding, confirming that we have beta antimony in these few layers of antimony. Okay, this was also confirmed by higher resolution atomic force microscopy, in which we can have kind of atomic resolution and the same lattice parameters. Okay. So yeah, this is just to confirm that we don't have any change in the composition, and using X-ray dispersive energy dispersive spectroscopy, we confirmed that we have just antimony as expected. And this is a very interesting experiment. Okay, when we were looking for small layers in this process, we found really small quantities of layers having this really small thickness, as smaller as 0.9 nanometers. So yeah, this should correspond with a single layer, of course. But in order to demonstrate that we have a single layer, indeed, Pablo did a very difficult experiment, which is based on he fold with the AFM tip. He fold this part of the layer on the top of the other bigger layers. Okay, and then he was able to remeasure the height in here, and what he observed is that we have a height of this part of the layer, which is 4 angstrom. As you can see here, this height profile corresponds nicely with the interlayer distance in the beta antimony crystals, confirming that we have, in this case, this part of the layer correspond to just one single layer. Okay, so yeah. Additionally, we confirm that our material has nice environmental stability. Let me show you this experiment. In here is we have the two initial layers immediately after exfoliation. We took a height profile along this green line, and yeah, we allow to stay this substrate for 2 months under ambient conditions. And then we took again the height profile, and we observed that nothing changed. And then we immerse this substrate into water, and then we remeasure again the height profile, and we observe no change, confirming that we have a nice environmental stability, because in addition, we were able to have a atomic resolution on the top of our layers. Okay, so yeah, so this was the first approach to isolate a few and single layers of antimony. And then we decided to extend the possibilities to form this, to isolate this material. And then we tried to do this isolation by using liquid phase exfoliation. In here, we start with the same, with the same crystals, beta antimony. And then as I told you before, you have to look for solvents able to, somehow assist the exfoliation of this structure. So yeah, and then you need to incorporate energy to the experiment in order to assist the final delamination of the material. Okay, and checking a lot of possibilities, we end up with this mixture of solvents as the most suitable one for delamination, isopropanol water 421, and then we end up with this suspension. And yeah, in order to get a more homogeneous distribution of the material, we submit this initial suspension to centrifugation. And we end up with this nice suspension, or even we can call colloid, because it was stable for weeks without showing any kind of material aggregation. The suspension showed thinner effect, so yeah, as expected. And then, but if we check the concentration, the concentration, which is 10 to minus 3 grams per liter, it was not very high. Yeah, in any case, we characterize the material that we got in this suspension by, for instance, atomic force microscopy. When we drop casted this substrate with our suspension, we observe that we have a lot of quantities of layers with the relatively large lateral dimensions, and with a step height of about all of them of about 4 nanometers. Okay, so yeah, we eventually have atomic resolution telling us that we have a nice crystal, nice quality of our material. That it was also confirmed using advanced spectroscopy and microscopy and spectroscopy techniques in collaboration with Maria Varela. In here, I showed you the STEM results with the atomic resolution and the ILS experiment, in which we confirm the composition of our material, which is based, of course, in antimony, showing kind of amount of oxygen probably coming from the solvent or partial oxidation, material oxidation. Okay. Yeah, we also use Raman in collaboration with Gonzalo Avellán to characterize our layers. And here you can see that, yeah, it's something not very usual. We were unable to detect any Raman signal. These are the two big characteristics of antimony. But if you check properly here, carefully here, we were unable to obtain any Raman signal below this thickness, below 70 nanometers. So yeah, and in order to understand these results, we, in collaboration with Janina, she calculate different structures of antimony, monolayer, bilayer, and so on. And comparing the results, she end up with this explanation in which you can see that, yeah, if you compare just the bulk situation and the monolayer one, so we observe by one hand something that we observe also in the experiments, is that the intensity of the signal dramatically decreased by a factor of 3. So yeah, 3 orders of magnitude, sorry. And then another important aspect is that she predict an inversion in the intensity of the two relative intensity of the two signals, as you can see here, from the bulk to the monolayer. So this signal become, is more intense than the one corresponding to the EG. So additionally, we observe a blue chip. All these, calculations agrees with the experimental observations. Okay. Yeah. Once we were able to obtain the material, we decided to try to do kind of chemistry. As I showed before, yeah, in these layers of antimony, we have something that we can use for the chemical functionalization of this material. Every single atom is connected to 3 neighbors, 3 antimony atoms, but every single atom has what I try to represent in here is a lone pair of electrons. So the layer should be electron donor. Okay. So yeah, the idea in here was in collaboration with Gonzalo Abellan and Andreas Hirsch, we were looking for a molecule with an acceptor electron molecule. Okay, and that's the reason why we were working with perylendiamine, this strange molecule, long molecule. Okay, and then we did the following experiment. So first, we took we produced by micromechanical exfoliation a single layer, so a few layers of antimony and located on silicon oxide. So this is the case. And then we treat this substrate with a solution containing the molecule, THF solution containing the molecule by drop casting. Okay. And what we observe from here to here is that we enhance increase the height of the initial layer by 3.6 nanometers, meaning that we have something on the top of this layer. So probably the molecule, we hope. And yeah, this is we try to characterize with using, for instance, a scanning Raman spectroscopy, and this is the result. So in here we have just the antimony layer. So we print in here only the peaks corresponding to the signal of silicon oxide. And as far as we have on the top of the silicon oxide, we have the antimony layer. In here, we observe a decrease in this signal, of course, corresponding to the location of our antimony layer. And then we treat this layer with the perylendiamine molecule. And then what we observed, it was that we have signals, Raman signals corresponding to this molecule, perylendiamine, on the top of the layer, of the initial layer. Okay, but this was also interesting because initially this molecule is a strong fluorescent molecule. So in order to be able to see these signals corresponding to the Raman of the molecule, you need to you have to assume that you have a kind of charge transfer between the molecule and the antimony. So quenching this strong fluorescence. Okay. So in order to confirm this charge transfer between the two components, antimony and the perylendiamine molecule, we carried out, in collaboration with Enrique García Michel, we carried out this complex experiment under the cyclotron radiation, XPS in synchrotron. So yeah, in here we prepare by micromechanical exfoliation different layers of antimony and we locate them on the top of gold. Okay, so Enrique called these layers as A, B, or C. And in here, I show you one spectrum of the one named as B. As you can see, we have in here, from the initial material, we have in here two interesting peaks. The one corresponding to metallic antimony, and that one corresponding to kind of antimony trioxide. Okay, so then we treat the sample with our molecule, yeah, and then we collect again the same spectrum after this treatment, and we observe by one hand kind of shift in the peaks. And if you analyze properly, you can observe that in between the two samples, we have a core level shift of about 0.4 electron volts, which is telling us that the perylendiamine molecule is acting as an electron acceptor, which is the experiment that we were looking for. So getting this interaction with the donor electron acceptor between the antimony and the perylendiamine molecule. In order to further corroborate this interaction, Janina calculate the absorption energy in between these two, the molecule and the antimony. And she ended up with this number, minus 1.27 electron volts, suggesting that we have a very strong interaction, taking into account that this is not a covalent bond, but just supramolecular interaction. Additionally, she calculated the change in the band gap corresponding to the antimony, initial antimony, and functionalized antimony. And what she observed is a shift in the band gap when we functionalize the antimony with this perylene D imine, that is about minus 0.8 electron volts, which is kind of in agreement with the observation that we did with XPS and additionally with Raman spectroscopy. And what is more even important is that is telling us, this experiment is telling us that antimony functionalization with different molecules could be a nice way to modulate its band gap. Okay, and then you can find interesting application for this kind of modulation, band gap modulation. So yeah, I know. Yeah, you probably, I think this audience is plenty of physicists and chemists, and I know you love to stay time looking for kind of fundamental observations. But yeah, sometimes one has to come to the reality, and that's the reason why we move further. And then we try to analyze potential application of these materials to real life. And then, yeah, this was the first experiments that we did in collaboration with Emiliano Martinez and Troy Banks from Manchester, University of Manchester, in which they were analyzing the potential applications of our antimony to form supercapacitors, okay? And for that, we use the liquid phase exfoliation antimony that we prepare, as I told you before, following this route. But in order to enhance the concentration of the final suspension, we introduce in here a new step. So before we try to sonicate the samples in water isopropanol, then we introduce a kind of ball milling, wet ball milling, using water isopropanol as protective solvents in order to reduce the size of the initial crystal. So it's a previous process that we implement before sonication. And the final result it was that we enhanced the final concentration by a factor of 10. So yeah, and then we use this new suspension with this higher concentration to modify what is calling this electrode. This is what is calling a screen printed electrodes. All these dispositive, and we were interested in modify, in particular, the working electrode. This cycle. Okay, and for that, okay, this working electrode in here is composed by something that they call printed graphite ink. So let me show you the scanning electron microscopy. This is the bare electrode. So you can see here kind of flakes of probably graphite or small fibrilized graphene, I don't know. And on the top of these flakes, we locate, by drop casting, we locate our small flakes of antimony. Okay, those are the flakes modified with the antimony on the top, and then yeah, this is a corroboration of that we insert in this positive antimony, and this is again corroboration by Raman. In here you can detect the peaks corresponding to antimony, in addition with those corresponding to a kind of graphene. And then we measure in here, we estimate first the capacitance using this, doing this experiment, which are based on cyclic pulse tomograms that we carried out at different quantities of antimony that we put on the top of the electrodes, and measuring at different scale rate. We observe in general that as far as we enhance the quantity of antimony on in the electrode, we observe that we decrease the values of capacitance of this system. So yeah, this was the optimal amount, 1.8 nanograms. You have to take into account that if you put more and more quantity of antimony, you decrease this value, because is the higher that we got is about 2 sorry, 8,500 Faraday per gram. So as far as you enhance the quantity of antimony on the electrode, you reduce the value of capacitance. So you have to find the suitable compromise in this modification in between the quantity of antimony that you add on the top of the electrode and the value of capacitance that you get at the end of the experiment. Okay, so yeah, and we end up with this high exceptional value of capacitance determined by this experiment, probably because of two factors. As far as you locate antimony on the top of the electrode, you enhance, you increase the electrochemical active area of the electrode by one hand, and by the other, you increase as well the electrochemical double layer over the electrode surface. So probably we have this nice result because of these observations, these factors. In order to get a more realistic value of capacitance, we perform the galvanostatic charge-discharge cycles, trying to avoid the contribution of, in this process, in the last process, in the other process, of the Faraday contribution. And then we carried out these experiments in which we observe again that the quantity of antimony, as far as you increase the quantity of antimony, the potential decrease. And we end up with that with this value of antimony at optimal in order to have a nice, good specific capacitance for our modified electrode, 3.6 nanograms. Okay. Additionally, you can observe that we have the modified electrode is pretty stable, so it's stable over 10,000 cycles, so which is quite remarkable. And finally, in order to put our results in a more broad context, sorry, something is going on with my pointer. Sorry, let me see. No way to solve it. Okay, yeah, probably now. Yeah, I'm telling you that we plot in here the Ragone plot between power density and energy density. In here, I highlight in yellow the result that we got with the different antimony experiments, and in particular for low quantity of antimony, we have exceptional values of power density versus energy density, telling us that we have a really high power supercapacitor in comparison with this long list of other 2D materials. Okay, so results were very promising despite we don't have a real dispositive. So because we have some problems to build up this big device, a big supercapacitor device. Okay. So then we also tried to implement graphene as in order to get kind of a sensor, biosensor. We did these experiments in collaboration with Encarnación Lorenzo from my university. And let me explain you this in detail, this scheme. So yeah, first for this experiment, we should redesign the production of our material, trying to get the material. I cannot move the laser pointer. Okay, the material by using just one single solvent, because we realized that the presence of water was kind of hampering our experiments. So we were able to produce by liquid phase exfoliation in isopropanol this nice suspension. This is just a material characterization by AFM, Raman, the whole set of techniques. And in here I showed you the first experiment, the first relevant experiment that we did in between our antimony and a single strand DNA. We tried first to evaluate the interaction between these two systems. And what we found is that as far as we increase in here we play with the quantity of antimony in order to get this plot and be able to evaluate the intrinsic binding constant of this interaction. As you can see here, we have a very strong binding, a very high binding constant, telling us that we have a very strong interaction between antimony and single strand DNA. This was the first step of the construction of the sensor. In order to get more details about this interaction, in collaboration with Juanjo Palacios, he calculated the interaction between a nucleoside monophosphate, these molecules, and the antimony. These molecules are composed of the nucleobase, the phosphate groups, and the sugar groups. Okay, so he was evaluating these graph summarize all the results with the 4 nucleobases, and as you can see here, in all the cases we have a strong interaction. So the absorption energies are strong, values are high. Okay, we have a strong interaction. But by the other hand, what he observed is that we have a kind of inspecific interaction. The meaning of that is that we can these molecules can interact by means of the through via oxygens of the phosphate groups, or oxygen of the sugar groups, or just the nucleobases. Okay, and this is important. I will show you why. Because this is the construction of the sensor, and you will see that we need kind of these interactions via oxygens in order to be able to detect to make the detection of our DNA sequence. Okay, what we try to do in here, we construct our sensor using this again this SPD device. So in here we have the scanning printed electrode, but in here we work just with gold instead of graphite, as in the case that I showed you before. So in here we have the working electrode is gold. Then we put on the top of this gold the antimony, okay? And then on the top of the antimony, we locate what we call a capture proof, okay? Which is this sequence of single-strand DNA. Is a sequence which is composed of 100 bases of DNA nucleotides, okay? So yeah, we put in that way. And as I told you before, from the calculations carried out by Juanjo Palacios, we expect to have a kind of interaction allowing to locate the nucleobases in that geometry, which is essential. So the location of the nucleobases in perpendicular to the antimony is essential for the next step, which is the recognition of the complementary sequence of DNA to the one that we locate on the top of antimony. I have to tell you that this sequence is an artificial sequence designed to hybridize and form double-strand DNA with and to detect a kind of gene associated with the breast cancer. Okay, so yeah, in here we use single-strand DNAs coming from real patients from the hospital, La Paz Hospital. And when you put the sensor in contact with these single-strand DNA sequences coming from these patients having this cancer, then we observe that you have hybridization, and then you have a kind of nice electrochemical response, and which is nicer if you compare the result that we got when you instead use this what we call wild type single-strand DNA coming from people without this cancer. So when you treat our sensor with this single-strand DNA, we observe a very different electrochemical response. So those are the real values. So in here you can see that when you use the sequences coming from the people having cancer, we have this electrochemical response corresponding to around 4 microamps. While when you locate on the top of our sensor just samples coming from people without this problem, so you have a rather different electrochemical response, which is around the intensity is around 9 microamps. Okay, so it's a big difference. So you can the errors are very small. So telling you that this sensor is very effective. And you can compare the efficiency of this sensor when this is the experiment, when we locate, when we use directly the sensor, sorry, the electrode without putting on the top the antimony. So as you can see here, the final result is telling you that you don't have, it's not very sensitive. The difference in between the people having the cancer with others without this problem is very, very small. So we don't have, we cannot use directly this electrode. Okay, so yeah. In order to finish my talk, I want to stress that yes, in order to go for applications, as I showed you, we're focusing on the use of liquid phase exfoliation, antimony coming from liquid phase exfoliation. As I told you, we in this kind of suspensions, we have little, this is the concentration, the typical, the higher concentration, but meaning that we have little amount of material into this suspension. So if you want to go for some kind of applications, for instance, the construction of this supercapacitor that I mentioned you before, you have to do something. You have to get the material in larger scale, okay? And in order to solve that, we were just trying to develop an alternative route to do that. And then we switch and we change the approach. And instead of using this delamination top-down approach, we changed to bottom-up approach. We do chemistry, and then we did this reaction in between antimony dichloride and this complex with the dodecaine thiol, this long molecule, this long thiol, and then we treat this solution with oleamine, with this molecule, this long amine. This amine becomes a reductor agent of the antimony 3, and then doing this reaction under hot injection conditions. The meaning of that is that you get this temperature 250 degrees for a short period of time, just few seconds, and then you observe formation of a dry material, which at the end I'm going to show you correspond to nano hexagons, few layers of antimony. Okay, if you do this reaction, yeah, batch by batch. So we observe that we have a non-scalable process. The meaning of that is that you are allowed to do the reaction only working with specific volumes of these, precursors. So hampering the production, the massive production of material. And in order to overcome this problem, we, in collaboration with Julio Gomez, where he designed this reactor, continuous flow reactor. He called Robustiano the first because his steel reactor is very robust. And then, we started with the same precursors, and we submit the solutions to this temperature for we adjust the flow to have this temperature for a short period of time. Immediately after, we collect the material and decrease the temperature. And the result of that is that we produce these nice hexagons. In here, this is the AFM, telling you that you have relatively large dimensions. We were able to produce hexagon up to 6 microns inside. And however, with relatively small thicknesses, about 5 nanometers. As you can see here, they show nice morphologies. Eventually, this is the transmission electron microscopy characterization. Eventually, we have crystallinity. This is the electron diffractions coming from this hexagon. This is the Raman, confirming that we have antimony, few layers antimony. And in here, this is the X-ray pathway diffraction, confirming crystallinity. Okay, but the question in all these syntheses is that we observe that as far as we are using these long molecules, these long thiols, at the end of the day, we form hexagons, but they are partially or fully sometimes covered by these long molecules. And this is a problem if you wanna, use these hexagons in order to, build up kind of devices. You have to establish, for instance, electrical contacts, and then you have to do something else. So, and in here I showed you that we were evaluating the use of different solvents in order to remove these files on the top of the hexagons. And I show you here just two solvents, the isopropanol one, in which we observed that we were able to remove the file, but we induce kind of oxidation. Okay, if you compare these results with the one that we observed, this is XPS in collaboration with Enrique Garcia Mitchell, with this, when we wash with chloroform, we observe that we have less oxidation, and then probably this material is more interested in terms of, potential uses. This was corroborated by electron energy loss spectroscopy in collaboration with Maria. And I show you here the full characterization using advanced, electronic microscopies, in which you will have a nice, atomic resolution. And we observe that we don't have much amorphous layers around the material, confirming that we don't have kind of oxidation or very few oxidation around our nano hexagons. Okay, and then we decided to use these hexagons, the one was with chloroform, to establish electrical contact. And here I showed you the two experiments that we did in collaboration with Julio Gomez and Diego Alonso. Under this configuration and this configuration, we observe, metallic behavior for our hexagons. Okay, but this dramatically contrast with when we use samples washed with isopropanol, we were unable to detect any current flowing when we contacted. This is the gold electrode, and then we use the AFM conductive AFM tip, and we were trying to push, apply a kind of pressure on our hexagons, and nothing happened. Okay, so yeah. Okay, I'm done, almost done. Just I want to tell you that this is the current situation about antimony. So apart of works focusing on material production, right now works trying to develop alternative use of these materials are growing and growing in different fields, energy applications in energy, sensors, even in biology. Yeah, this is just to show you the evolution of the field. In this year, we were able to produce antimony for first time. Before it was just theoretical calculations. Those are citations per year. And then you observe that the field seems to be still of interest for researchers of different nationalities, and still we are working in this field with harder competitions with Chinese harder competitors from Chinese, but still we can do something in the field. And just to summarize the works, the 400 works that have been published, apart from material science, physics, and chemistry, the number of works in other disciplines showing the potential use of this 2D element is becoming more and more. The number of works that appear are more and more. This is the take-home message. Is antimony is a new allotrope of antimony that show exciting properties. We are trying to demonstrate some of them still. For instance, this topologic behavior. But however, still there are a lot of work to be done. I have to finish my talk giving thanks to people of my group working in this particular field, Íñigo, Carlos, and David, and collaborators, strong collaborations with Julio Gomez and Pablo, and also students, Diego Alonso, and of course, a lot of collaborations that make possible all these results. And yeah, again, the whole group, thanks to all the students, and in particular those involved in the antimony field. And thank you for your kind attention. But sorry, yeah, that's right. If you probably you read my abstract, and for those that read the abstract, probably you realize that something was missing in my talk. Is around this concept. I was using this approach, the delamination, to show you that we can produce, for instance, antimony, starting with these laminar crystals, these van der Waals crystals, using delamination. But the question is not so simple when you start with a kind of 3D crystal. Let's say diamond, for instance. So if you start with diamond, the question is, can you produce kind of nanolayers? And just to show you something coming from the press, we recently proved that it is not strictly necessary to start with a layered material to end up with a nanostructure, 2D nanostructure. And in here we demonstrate that it is possible to work with a diamond-like structure. This is alpha-germanium. And using chemical forces, we were able to delaminate through via specific planes that I show you in here very briefly, and end up with suspensions containing these small nanolayers of alpha-germanium. And for you physics, I think this is a nice message, because we observe that when we play with the thickness of this nanolayers from germanium, we observe that we can modulate the band gap of this material. Okay, but if you want me to talk further, you have to press in here just for vote me for the next IFIMAC talk, and I will be very, very happy to explain you more details about that. So thank you very much. Now it's time for questions. Thank you.
Thank you very much, Felix, for the very nice talk and the very nice ending. We will keep the answer for some other moment. Okay, so the session is open for questions. So we have some time before lunch. So if you have any question, you can just unmute yourself and just make the question to Felix. I see a hand. So please, Ivan.
Hi, Felix. Nice talk. I have seen that at the end of the talk, you show some results where you were able to form antimonene from top-down approaches. But I got the impression that the thickness was relatively high. I mean, it was something like 5 nanometers or something like this, at least one profile that I saw. Which is the thinnest antimony layer that you can grow? Is there any limitation, or is just that it's difficult to find them and to characterize them?
You mean this sample?
Yeah.
I mean, as far as we are trying to produce bulk, this material in bulk, I mean large quantities. Not bulk, but large quantities. What we observe is that it's not trivial to adjust the experimental conditions to decrease the thickness. So probably 5 nanometers is the smaller, flakes that I don't know, maybe we found something like 3 nanometers sometimes, but not all of them, not statistically, but you can find eventually. I mean, in a sample, you can find some flakes, small flakes, but just few of them. It's complex, because if you focus on this reaction, as I told you, this is a flash reaction, and as far as you enhance the temperature up to 250 degrees, then the time that you have in order to reduce this temperature in a short time is not trivial to adjust. And then as far as you open this window time, then you enhance the thickness. So we want to do something. I mean, this is a big problem. We want to do something, in order to go down, but still, yeah, we are playing with the experimental conditions.
Okay, thank you.
So, more questions. I had one, Felix, about this supercapacitor, you call it. So you saw that your antimony in this plot of energy versus power, it seemed to be the most tunable, no? The rest of the materials were flat. All this, so is
Yeah,
this
yeah,
you
exactly.
control over the concentration, or this is because the material is this
Yeah,
relevant?
this is, I mean, yeah, you're right. I mean, apparently, yeah, we have good expectations. In here, we just play with the, let's say, the amount of material on the deposited, modifying the electrode. Yeah, indeed, what we have to do now is to try to build up a real supercapacitor. For that, you need a large quantity of material. The smaller you can build up needs like 200 milligrams. So at that time, 2 years ago, 3 years ago, we were unable to provide with this amount of material. Yeah, and now we hope that using the antimony that we can produce by bottom up by chemistry, we can end up with a real supercapacitor and determine properly this power density and energy density of the real capacitor. But as you said in here, yeah, our in here we plot these values playing with the concept with the amount of antimony, and here we have two exceptional values. And as you said in here, when they play with the amount, you have to take into account that probably in here you have just 2 points, and here just 2 points. Yeah, this I don't know the reason why they plot just 2, or they don't collect experiments with more. But in here they have many points, and in principle, yeah, something is much better for our material.
Yeah, and the slope is different and it's much flatter for the rest of material.
Yeah, that's right.
Remarkable. Okay, thank you, Felix.
Probably is yeah, you're right. Probably yeah, is connected with the interaction between the graphite and the antimony. I realize now that we were observing this in another experiment, that there is kind of a specific interaction between both materials. So I don't know whether we have kind of a donor-affector interaction.
Okay. Well, thank you, Felix. So I don't know if there's.
Hello, can I have one question?
Yeah, please.
Hello, very nice talk. And this is Benny from University of Manchester in UK. And interested in this germanium talk, germanium work, because obviously this is no longer a layered material. But yeah, I mean the very last slides, to be honest.
Yeah, you have to vote. I'm gonna say nothing. I'm gonna say nothing.
well, I did click, but it doesn't respond. Yeah, I mean, because this is not a layered material, and I can imagine, and the bonding energy or the bonding density can make a difference. That you can probably break some bonds, but
exactly. We calculate in collaboration with Juanjo Palacios. We calculate the different energies along the several cleavage planes, and this makes the difference, of course.
Oh, okay. Kind of the aspect ratio of this exfoliated layers.
Sorry.
Kind of the aspect ratio. I mean the lateral dimension and the thickness.
Yeah. You have a look. Yeah, we have like more than 2 orders of magnitudes in between the thickness and the lateral dimensions.
Oh, that's very, very.
That's the reason why we call nanolayers. Otherwise.
Yeah. Because I mean, I would imagine it's like asymmetric dot. But it's actually a flake.
This happened. We tried to do the same with the following element. I mean, no, the one on the top. We tried to do the same with the silicon.
Yeah.
And then still is what we found is what you said. I mean, we found like we were able to have just a slight difference between the lateral dimensions and the thickness as smaller as 1 order of magnitude. And we couldn't adjust all the parameters. You have to take into account that there are so many experimental parameters that it is extremely difficult to find the suitable conditions. On the other hand, take into account that when you apply energy to either germanium or silicon, you apply energy and you have oxygen, and then they easily oxidize and form the corresponding oxides. So it's you know, you have to play with a lot of experimental parameters, but we were able to do that for germanium and not for silicon.
Okay, okay, thank you very much. I have read the paper in details. Thank you very
No,
much.
just both me.
Thank you, will do.
Thank you very much. So I think it is already lunchtime, so I think we can finish. Let's thank again Felix for the very nice talk, and thank you all for attending. I remind you that we will have another seminar next week. It will be Peter Sol from Amsterdam, the University of Amsterdam, and he will be talking about colloids, the design of colloids in the nanoscale. So thank you very much, Felix, for the very nice talk, and thank you all.
Thank you and the audience, of course.